Welcome, Hornets. In this video, we're going to continue talking about areas under a curve, but we're going to start connecting it to the idea of sums. Because ultimately, what we're trying to do is add areas together, and these can be written as sums with a pattern. For example, we started talking about an upper sum and a lower sum in the last video, and so I'm going to do the same thing. To find a lower sum, we're going to work with this left value here. And notice that between the two sides that make up this rectangle, one side is taller than the other. That lower side is going to be the inscribed rectangle. The taller will give me the outer or circumscribed rectangle. Now, as we talked about before, the upper sum is made from the circumscribed with an equation that is like this, and we have the inscribed giving us a lower sum. Now, if I'm working with this, that means that I can look and find this value in between. Notice our delta x is 3 minus 1, and I have 4 intervals, which means I'm looking at 1/2 is the gap between each of these lengths on the rectangle. So this x value is going to be 1.5. 2 is right there. And right smack dab in between 2 and 3 is the 2.5. This height is therefore going to be f of 1.5 . This height right here, 2, 4. Then we have this height right here is 2.5, f of 2.5. And we'll need to know what those values are as soon as we start to try to find our total sum. Now you'll notice, if I'm working with this left side, that I need to work with my 1, which is going to be our x sub 0, where we haven't moved yet. This is x sub 1, x sub 2, x sub 3, x sub 4. And we want to work with just the first 4 as opposed to the last 4. Notice the last 4 give us the heights of the upper angle. So what we want to do is we want to start connecting this idea to summations or sums. After all, I have my length, which is 1/2, times my height at x sub 0, plus 1/2 times my height at f of x sub 1, plus 1/2 times my height at f of x sub 2, plus my height at f of x sub 3. Now, if I'm working with summations, I want to factor out the 1/2 and look at it. I have f of x sub 0, f of x sub 1, f of x sub 2, and f of x sub 3. Now, ideally, I'm going to put this into a common form. So I'm going to have a summation that uses a variable I and starts at 1. And it goes up to my n equaling 4. But in order to start with the 0, I'm going to have my x sub I minus 1. Now, this gives us our lower sum, and our upper sum would have the f of x sub 1 plus f of x sub 2 plus f of x sub 3 plus f of x sub 4. And this would be 1/2 times the summation as I starts from 1 up to 4. But now it's not f of x sub I minus 1 starting at 0. It starts at 1. And that's x sub I. Now, if you recall, in my previous video, I was saying that there is a random x, which we call x sub I, in between. And this is going to be evident as we start increasing the number of rectangles that we have. But this is the general idea. Having two sums, one that is greater and one that is less. In this case, I minus 1 less than the actual integration from a to b, which was 1 to 3 of x squared dx, which is less than our 1/2 summation of I equaling 1 to 4 of f of x sub I. Now, we want to keep going with this because at the moment we haven't put our function in. See, we know our function. Our function right here is an x squared. So we should be able to use x squared with our x sub I. And we've talked about that x sub I as our c sub I. So let's just go ahead and look at that. 1/2 the summation as I goes from 1 to 4, and we're looking at x squared, where we have 1 plus our delta x happening I times, and that I is starting from 1 to 4. And we want I minus 1 for the lower. Then we have integration is in between. Oops, let's go from 1 to 3. X squared dx. And then we have our upper sum. Now you'll notice the way I'm writing this, it's actually a squeeze theorem if I can create a limit with it. Oh my, creating a limit. Wonder how I'm going to do that. 1/2 I squared. Okay, well, let's just think about it. In order for me to get a better approximation for my area, I have to have more rectangles. The more rectangles I get, the closer I get to the actual area. I have one that's too much and one that's too little. So one is getting closer to the answer from above, and one is getting closer to the answer from below. And slowly they're pressing together, and at infinity, they should all be equal. So I should be able to take this to infinity. The limit as n approaches infinity for 1 over 2, the summation as I starts at 1 and goes to n, which is going to infinity, of 1 plus I over minus 1 over 2. And then I have my squared. Does that look right? No, it doesn't. Why not? Because if I've increased my n, then my delta x has changed. And the delta x, if you recall, was that 3 minus 1 divided by 4 when we had 4, but we've now changed it to an n. So that's not going to work too well, is it? we need to change this to 2 over n. That means that this has to change into a 2 over n as well. And I have now 2i minus 1 divided by n. And now I have a correct limit. Notice how when I altered the number of rectangles, it worked with the denominator. Less than, equal to, 1 over 3 x cubed dx, less than. Now on the other side, the same thing is going to happen. Remember, we still have 2 over n here. So I'm going to have 2 over n, the summation as I goes from 1 to n. But now I have only 1 plus 2i over n squared. Now, this is our upper sum is this one here. Our upper sum is working with c sub I, which is 1 plus delta x times I. Our lower sum is this c sub I minus 1, which is found by 1 plus delta x times I minus 1. And smack dab in the middle is the actual integration, which at infinity is equal to all three. Now make sure you understand that. Because if they're all three equal at infinity, I suddenly have a choice of which one I want to work with. Do I want to work with that lower sum, which has that binomial in the numerator? Or do I want to work with just a straightforward monomial in the numerator, which gives me a binomial to FOIL? This is going to ultimately give me a trinomial that I'm going to have to FOIL out. And trinomials are harder to work with. So if I have a choice, I want to work with my upper sum and c sub I. Okay, let's just take a look one more time. We talked about an upper sum and a lower sum, how they work with one side or the other. We took x squared, broke it from 1 to 3 into 4 segments that were at 1, 1.5, 2, 2.5, 3. I know that if I were to make the area of this, it would be the lower sum would be 1 half x sub 1, 1 half x sub 0, plus 1 half x sub 1, plus 1 half x sub 2, plus 1 half x sub 3. Factor out the 1 half, and I just have this series, which I can write in sigma notation. Sigma notation starts at I equaling 1 and goes to however many intervals. We have 4, so 1 to 4, but I have to start at 0, and go to 3, and that makes I minus 1. The upper sum did the same thing, except it worked with 1, 2, 3, 4. That's x sub I. And because I had my lower sum and my upper sum, I put them together with the integration in between. And this is where we start to think about this as the function with the number of increments in terms of I minus 1 and I, which we can then simplify for our upper and lower sums. Now we could find these values by working with the table of values and just multiplying the length times the rectangle. We'll see that next. I hope this has helped you to see that upper and lower sum. I hope this has helped you to recognize how we can change things into a series and potentially write it in a general term. Thank you very much, Hornets. Be well and be safe. Take care.